in the group 4, right? And then in group 5 we have phosphorus, which is very important, and arsenic. Gallium is also in group 5. So what are the elements in group 5? Can you please say?
Nitrogen, phosphorus, arsenic, antimony, and
Okay, antimony is AB.
SP.
SP. Okay. So anyways, these are some of the materials which are some of the elements which are in group 3 and 4, 3, 4 and 5, and they are really important because most of them are used in semiconductor IC fabrication, and they are considered semiconductors. So they are in the middle of conductors and insulators. So conductors are, for people who has a biological background, just to give them some perspective, conductors are the materials which can easily conduct electricity. And by insulators, if there's a perfect insulator, if you apply voltage, you will not get any current flow through. So talking about here, if we talk about silicon, that's a very commonly used material in semiconductors. And then we also have a boron, we have a phosphorus. So these are very commonly used. So why silicon is very important for IC fabrication? The one reason is in the silicon is because a semiconductor, you can dope it with external materials. For example, right now it's not a conductor, but you can dope it with extrinsic materials, for example with the boron or phosphorus, and then you can control its conductivity. How that works is silicon has 4 electrons because it's in the group 4 in its outer shell, and once you make a crystal, or the silicon is combined in a crystal with another silicon.
Yeah, this is tricky. You have to be, when you see it, when you're making the paper, it's not.
Oh, okay, got it. Sorry. Yeah, no, I'll take care of it. Okay, so now the silicon making a covalent bonds with other silicon, and there is also a silicon atom here, so which also shares it. So these are the covalent bonds. So in this structure, now if you put another like phosphorus in here, so phosphorus have 5 electrons because it's in group 5. So what happens is that this one is shared with this one is shared with this one. These are 2 more, and then there will be a silicon here because this is the impurity. But phosphorus have 5, so this will also be shared with another silicon. So the 5th electron will be freely available, and now based on how many phosphorus atoms are there in this structure, you can have some number of extrinsic electrons available which can control the conductivity of a material. For example, if your doping level is 10⁻⁵ phosphorus atoms in this structure, in that case you have a conductive semiconductor material which is good conductivity, and now if you decrease that doping, so you have less number of electrons available. So in that way you have much control on the material conductivity, which you can, for different purposes, you can change the doping level, and then you can have the material of some specific conductivity or insulation. Okay, luckily it got started, so we'll just switch back in a second. And we have now, this is electron. We also have holes available. When we have a boron in here, it has 3 electrons. It's in the outer shell. When boron is doped into a silicon structure, in that case, now suppose this is not phosphorus, this is boron. So what happens is that, so this electron will not be there anymore, and the silicon will be sharing providing only 1 electron, but because boron doesn't have, so there will be 1 hole. So I'll put H for hole. So hole is considered as the absence of electron. Now once you apply voltage, what happens is that any electron in the system can easily enter into this hole because it's a positive charge. So hole is just the absence of electron. So in that way you can still control the conductivity, because if there are a lot of holes, so then electrons can flow into those holes, and then So for example, if the electron is flowing from here to here, so one way you can consider although electron is going to fill up the hole, but hole is also getting, so there will be hole in here then. So in the other way you can say the hole is traveling also.
What is hole?
Hole is absence of electron. So once you have a complete 8 electrons, then it makes very stable. But if one is absent, it means any electron can easily come there to fill up the hole. So that's another way it can introduce the conductivity into the materials.
Are they an actual like charged species, or is it like
It's considered positive charge.
like an electronegative attraction?
It's just the absence. There is no electron, so there will be a equivalent positive charge there. So that's why electron can go there. So the good thing about the semiconductor is that you can change, or you can use different dopants, which can be either from group 5, which will be N dopants, because they produce electrons. They provide excessive electrons to make the material conductive. And it can be from group 3. So you can have a P-type. They are P-type dopants. So you can make material which has a lot of holes. And why we need that, you will see.
Can you understand this hole as like the outermost shell is deficient of electrons?
Yes.
And to fill up the outermost shell.
From another, because once, from another atom, the electron will jump into the system. Okay, now we'll switch back to laptop. Okay. So here was all the elements in a right form. And we have carbon, silicon, germanium, and tin, and lead and other materials in the group 4, which I was talking. So I'll just jump from there. So, and you can see these silicon and germanium are very commonly used in semiconductor. And then there are compounds. They're also available in compounds where, for example, the gallium arsenide or aluminum phosphorus, they're also used for different applications. And this gallium arsenide has very good optical properties and used for high frequency applications. And they are also available in 3 compound forms, where 3 of the semiconductors make up one material, like aluminum, gallium arsenide. So in that way, they have some typical, you can modify some of the properties, and they can be used for different applications. Okay. We briefly talked about I just won't go through it once again, about the extrinsic semiconductors. And here you can see they can provide extra charges, change the conductivity. So N-type dopants, which provides the one extra electron, P-types, which provides the hole to the silicon structure to make it more conductive. So what happens when it applies the dopant electron? For example, in here we are doping it with the phosphorus, which is a group 5 element, and it produces the extra electron. So, and then you require less energy to move that electron to conduction band. So in other words, you can control the conductivity of the material. And same now, if we use a boron or aluminum gallium from group 3 elements, then you have an extra hole in here. If this is the impurity in the system, then you can control again the conductivity of your impurity. Then you have one extra hole in this structure. So, and that hole, you can move electrons into that hole. So in other words, impurity is something, because if a silicon structure, so silicon is a crystalline form, so there is all silicon atoms. So whatever is considered into dopants, so that is all impurity into the system. And now we'll talk about the different type of structures which are available. So for example, the one thing is called the amorphous structure, where all the atoms are there but not in an organized form. So there is no order. So, and that's silicon is also available in amorphous form, and it has some applications. Silicon and other materials are also present in the polycrystalline form, So in polycrystalline form, there are certain regions which are in ordered structure. So you have a certain regions where you have a crystal, but in this structure, if you look at the whole structure of that material, then it's not a crystal. So if there are no boundaries and the whole structure is in organized form, then it will be crystal. But this is a polycrystalline. So you have poly mean multiple crystalline boundaries. And this is a conductive because if you apply voltage, then the electrons can flow through these boundaries. But if you have a crystalline silicon, that's not as conductive as this one. And then you have a crystalline materials where all the atoms are in organized form. Silicon is a crystal. You might have seen salt, NaCl, that's also crystal. You have Na and Cl atoms in a crystalline form, and that's why when you see it, it looks like a very transparent crystal structure. And there are some of the uses like these based on the form. All this is silicon, but you can have different properties from the same material based on how those atoms are arranged. For example, polysilicon, as I mentioned, is a conductive. All this is silicon. It is used for making wires in the transistors, so it can use as a conductor. So aluminum, you are familiar, that's a conductor. But polysilicon also is silicon, but it's also a conductor. And then amorphous semiconductors are also used in thin film transistors for displays. Okay, now when we talk about crystal, then there should be some ways to organize different materials into a different crystal system, because the crystal is a one terminology where we have organized atoms, but the crystals can be of different shape. So there are, in order to organize those crystals into different types, so there is a system is called the Brevis lattice. So it's arrangement of atom molecules in crystalline material, and the location arrangement of the atom will show whether it belongs to a cubical crystal or a hexagonal crystal. So these are all those 14 different crystal forms which are available, and all the materials which are out there, they follow any one of them. So if we talk about the first one, which is a cubic, which is simple cubic. It's a cube, so you have 8 items in there, and they are arranged in this format. So it can be a body-centered cube. So it's also a cube. So cube, you have all those lengths equally distanced from one another. That's how you make up a cube. But if it is a body-centered, it means there is another atom in the middle of that cube when you look in the structure. So that's the body center. So in that way, there is a face-centered cubic. So where you have a cube, but you have one atom on all 6 faces. So if you look at a cube, it has different faces, like front face, back face, right, left, top, and down. So those 6 faces, it has one atom in there. So in that structure. So there are different types of crystalline structures which are out there. Unit cell. So it's a tetrahedral. It's also called the diamond structure. So unit cell, if you look at the crystalline material, the whole crystal, so in there, the unit cell is a small section of that crystal. If you repeat that, you can make up the whole crystalline form. So it means the small section of the big crystal, that if you repeat, you can make the full crystal. That's called the unit cell, like a building block. And each crystalline form can have more than one unit cells. For example, in here it shows 2 different unit cells. This one, if you repeat it again and again, you will get all the map. But now if you consider this one as a unit cell, still you can repeat it and can make the whole structure. So both are the unit cells. So the one which is the smallest one, that's called the primitive unit cell. Now let's talk about if we have, now in a crystal we have different atoms arranged in a way. So if you want to access that atom just by a distance rule, you can have a radius r, HA, KB. For example, if this is a point and you want to access this and that point, so HA and KB means it can be 1 or 2. These are integers. So you can access any point in a crystal structure. So primitive cells are the smallest possible unit cell. So as I mentioned, the unit cell can be more than one. It can be a small, a bigger one. The smallest one is called the primitive cell. Now let's talk about if we have a cubic crystal structure, then it's very important sometimes to calculate the density of atoms, how many atoms are there in that crystal. For example, in this case, we have a simple cubic Brevis lattice, and let's count how many atoms will be there in one unit cell. So as you can see, there will be 8 atoms on all 8 corners, and because in a crystal, each atom is shared with other crystals, so in that way, each in one unit cell, there will be just 1/8 of that atom, that corner section, that will be a part of that unit cell. So 8 corners multiplied by 1/8. So in other words, you have a 1 atom per unit cell in this case. So let's do a little bit of exercise. Now, for example, if we have a body-centered cubic Brevis lattice in a crystal structure, how many atoms will be there in that unit cell? 9. No, but how many atoms per unit cell? So there will be 9 atoms, but in terms of whole atom. 9 in the big. 9. You have parts from.
So 9. So 1. Is that what you're asking about?
Yeah.
Okay.
9 is not the right answer, because the ones which are at the corners, you in a unit cell, you are not taking all of that atom. For example, in this case,
Oh, you're splitting it up between the 8 of them.
8 of them which are attached with the other
So
crystal,
one
because
and 8, or
so it will be. First of all, it's a cubic. So you have, okay, no, I cannot write it. So you have 8 like here, 8 into 1/8. So there will be 1 atom per unit cell in a whole atom, and then you have 1 in the middle, which is called body center. 1 in the middle. So you have 2 actually, right? And in that way, there can be a face-centered. So all those 14 different forms. So there can be a question in exam, like I can show you crystal structure and ask you how many atoms are there. Just make sure it's important. So this is body center, which I was talking about. Yeah, just do some practice. There can be a small question from there. Okay, it can be face center, it can be tetrahedral, so some different structures, and then you have to count how many atoms are there in the structure. Now I'll show you how NaCl looks like. So as I mentioned before, there's a salt, and where you can see all those NaCl atoms are arranged in the structure. So that's also a crystalline form. It's available in crystalline form. In the silicon, it's a tetrahedral structure where you have all those. If you look into 2D, you have a silicon atom, and it is sharing 1 electron with the other silicon atom, so making covalent bond. So each silicon atom is connected with the 4 others. So in that way, it makes a complete crystalline structure. And how the 3D lattice looks like is a little bit complicated. You have 8 at the sides. Then it's also there is a 1 1 on the faces, and there are also 4 in the middle, because it's a little bit complicated. So you have 8 at the sides as a cube, and then you have on the faces you have 6, and then there's also 4 in the middle. So it's a little bit complicated structure, but this is how it looks like, the 1 unit cell. So now crystalline planes are also very important. When we talk about different planes, for example, the X plane, the top one, the blue one. So you have X, Y, and Z. So 0, 0, 1 means that you have that plane in this direction. So you have 0, 1, 0, this plane. So 1, 0, 0, it is showing a different plane. So there can be, when we talk about the silicon, I'll show you later on. So there are some wafers which are cut into a different plane. So plane is, for example, 1, 1, 0 plane. So you have X is 1, Y is 1, and Z is 0. So, and then 2, 0, 0 plane, and so in that way you can have different planes into the crystal structure, and you can then see how many atoms are there which are touching that plane. And why it's important you'll see in a minute. Now the question is how we can identify different planes and directions with the crystal structure. So there is a way, it's called the Miller indices. By using that, you can calculate different planes into the crystal structure. For example, if we consider this example, so there are 3 points. If you want to calculate, okay, if we combine all these 3 points, so what would be the plane at the end in the system? So there is an easy rule. So just first look at the intercepts. For example, it is cutting 1, A at 1, B 2, and C at 4. So just put 1 to 4. Take a reciprocal of those numbers, and then multiply by 4 to make it so that everything becomes integers. So then it becomes, if you multiply every number by 4, then it will become 4, 2, 1, and then you can close into brackets. So that will be a plane of that map. So now if someone asks you what's the plane in here in this form, so you can say it's a 4 to 1 plane. So it means it's cutting 1 intercept at A is cutting 1, B at 2, and C at 4. And in that way there are different planes in the system. So it can be a 1, 0, 1 plane. So it means it is cutting x-axis at 1, y-axis 0, and z-axis at 1. So in that way it can be a plane structure. If you put instead of you putting 1, 1, 1, you can, if you put minus sign, so it will be a same plane, but it will be in the other direction.
Can you go 2 slides back? I don't have the next one. Where you were telling like select how this number 2.
Mm-hmm.
Can you explain how?
Sure, 1 second. So for example, if we have, okay, I'll go back to this one so you can see it. Okay, for example, if we have a cube, okay, so let's assume this is a cube. So it has different faces. So for example, if I want to talk about, so it has a x, this is y, this is z, okay? And then let's say you are talking about the front face, which is this one. So if we talk about that, it means it is cutting x intercept at, let's say, at 1. And then this one is parallel to y-axis. So if you look at just the face in a cube,
Halfway, right? Y is considered as a y-axis.
which one? This one? So you can consider anyone as a x, anyone as a y, anyone as z. So let's assume this is x, this is y, this is z. It can be other way. It depends on how you look at it. And then this, if you, let's say it's a continuous, and this plane, the front plane, I'll just give it a shadow so you can see it. So this is cutting x-intercept at 1, right? But it is parallel to y and z, right? Because if you see, it's just a one face. So it will be parallel to y-axis and z-axis on top. So then, because it is cutting this one, so you can consider it a 1, 0, 0. That's how you represent a point in a coordinate system. Because now you're talking about the plane, so it's like 1, infinity, infinity. Now we'll go back that once I was talking about the intercepts, because it is cutting x at 1, y at infinity, and z at infinity in this case. And then I was saying, according to the rule, you have to divide it by 1. So it will become 1 by 1, 1 by infinity, 1 by infinity. So it will become 1, 0, 0, right? 1 over infinity is 0. And then you close in the brackets. So now, if someone say, where is the 1, 0, 0 plane? So you will say, okay, this is a 1, 0, 0 plane. So just to understand it, where exactly it's talking about. Now when someone says, where is the 0, 1, 0 plane? So now you can understand that's a plane which is parallel to y-axis. Oh no, which is cutting y-axis and parallel to x and z.
Wherever it is cutting, that is number one.
That is number 1. And now the number 1 can be 2. So what will happen in this case, now it's the same plane, but now it's a little bit towards x, like more towards x. So that would be, this, for example, this is 1. So now you have another box here where it is cutting at 2. So that will be 2, 0, 0 plane.
So the second which, like, if we continue to draw, so the next one
Will be 3,
two
2 and then 3. So in that way you can, so it's
the
just,
lattice
it,
structure will
in a lattice structure, when you have a crystalline form, so everything is crystal. So considering any point as a region, so this is how you can say, okay, this is one plane, this is another plane. So if you now you want to look at a plane which is, like for example, if you want to look at this plane, right? So which is cutting all 3. So I'm making this triangle. Right? Can you see it? So this triangle. So let's say it's cutting all 3 at 1, 1, 1, right? So that'll be a 1, 1, 1 plane. So it just shows you in the system crystal structure that how. So you have to understand there are certain planes and how you can represent them into numbers. Okay.
But then for the other thing that you were talking about in your slides, you multiply that by 4, so it just be 4.
Because there was a infinity at the bottom, so that's why we didn't multiply it. But if it is some number, then you have to multiply with the number to make everything as an integer. Okay, I have to switch back now.
like we
So you can talk with me after this lecture more if you have any question. And I can really understand because there were basics in semiconductors, how you plan structure, and you can just come to office hours if you have any question on that, and I can explain in more detail. Okay, why we need to use the Miller indices? Because the silicon devices can have different orientations. For example, when you have a whole crystal, now the question is from where you want to cut that crystal, and in certain angles, and how you want to grow that crystal. So if you have a base silicon, seed silicon, when you grow it in one angle, then it has a higher growth rate as compared to the other direction. And the same if you have different orientations, the etching, when you do the etching, when you etch some wafer, it etches more into one crystal direction as compared to the other one. So that's why these directions are really important. I'll show you one example, the oxidation rates. So this graph shows oxidation rates of silicon. If you look at here, it's a silicon 100 plane, which was, for example, this one I showed you. And then you have a silicon 111 plane. And although it's the same material, but when you oxidize the material, you have more oxidation when it's facing 111 plane as compared to the other plane. So that's why planes are important when you want to calculate the rates, how much time you want to put your wafer into oxidation furnace to grow how much of oxide. So there you also have to see which direction is exposed. So in that way you can calculate the right number. So these plane and their directions are really important. And if you look at, this is how silicon, when it's grown in a big ingot rod form. And then you can cut the silicon into these wafers, like small slices in this direction. So then it becomes a wafer. So this is a wafer of silicon. Then you can build your devices, you can build your microfluidic structures on top of this wafer. So it depends on which purpose you want to use this
they
wafer.
always cut in the same way.
Yes, you can have you can cut into different crystalline forms. So, but this is how it looks like, the one wafer. Okay, now if you have a wafer, for example, if it's a 100 wafer, if you want to break it, you can break it in a certain angle. Then it's very easy to break. Then if you have a diamond, if you just put a scratch and you break it easily. But in other direction, you cannot break it. And that's because how it was cut before. And this is one of the process which is used to grow this whole ingot, the big silicon rod. And how they do it, basically they have molten silicon in the big furnace in here, and then you have this silicon ingot, so which has a rod and a small silicon crystal is attached in there. So this moves, this rod rotates in the middle, so you have a very high temperature at the outsides, but close to this ingot you have a low temperature. So it pulls very slowly. All this, when it's revolving and pulling very slowly. So what happens, the silicon becomes molten towards the outer side because high temperature, but when it becomes close to that rod, it start making bonds because it has to be molten form, so that it became bonds with the other silicon to make a crystal. And now how much fast you are rotating, based on, you can control the diameter of the wafer, which will be at the end. So for example, if you are pulling it fast, the silicon rod which you will be getting at the end will be of a small diameter because you are pulling it fast. Now if you are letting it stay for a longer time, then it can be so in that way you can control it. And then, so that's why you have wafers which are available from 2 inches to 12 inches. So you can make wafers of different sizes, and then you can cut it later on. And then the wafers also have, if you look at the real wafer, it has a cuts. It's not totally circle, so you have a cut somewhere which shows which plane it was cut when it was cut from ingot. So for example, in here it's a primary flat cut, and there is a secondary cut, that's a 110 N-type wafer, which also tells you whether it was doped with some impurity or not, like N-type or P-type. So by just looking at the wafer and the cut, you can tell what type of orientation this wafer was cut and if there is impurity in the wafer or not.
How can you calculate impurity?
No, you will not. They will give you numbers. So because once they have done some doping, so they'll give you numbers. Okay, we doped this thing, but just looking at the wafer, you can at least tell there's a P-type or N-type. And then they have a data sheet from here. You can get the numbers, how much impurity was added at that time. Okay, now we'll talk about the silicon, different silicon processing. And there are different processes. The first we talked about was how you can grow silicon, and then how you can cut into different wafers. And now once you have a wafer, in order to make structures on it, let's talk about just the transistor. If you might make a transistor on that silicon, what are different processes which are used? So these processes are similar processes which are used for microfluidics, and some of the processes are also used in making nanoparticles and nanostructures. It's just based on how you want to use that process. So in here we'll discuss is how you can use that process for making a transistor. So now the whole process, how it looks, how it works, the flow is, first you have to clean it, you etch it, you do deposition. So cleaning is just you clean with some chemical. Etch is you use some chemical, for example hydrofluoric acid, HF, it etches silicon dioxide, and it also etches if there are some impurities on the organic impurities on the surface, so you can use that to etch the surface. And there are different type of etchants which are available if you want to, if you have a structure which has a silicon and silicon dioxide, and you only want to etch silicon, not silicon dioxide, so there are etchants also for that purpose available. So we'll go through what are different etchants and how you can use it for making structures. So deposition is a very general term where you deposit different materials, and there are different phenomena out there. One thing is called the chemical CVD, chemical vapor deposition, where you have a wafer, and then you, for example, if you want to deposit gold, so you make vapors of gold, so they will come and stick to the surface. So that's the chemical vapor deposition. There is also one called physical vapor deposition, where you just physically make vapors and it just comes to, and you can use a heating or an ion beam to just heat up your target, which you want to evaporate, and once it's evaporate, it start depositing on your wafer surface. So we'll go through it briefly later on. And in that way you can deposit platinum, gold, or silver, or whatever you want to deposit on your surface. So, and you can use that deposition for different purposes. And now let's, for example, when we talk about we want to make a small electrodes. So for example, if we want to make the two electrodes, so for example, this is the one and this is the other one, and we want to control this thickness, and we want this thickness to be 50 nanometer. Okay, so just think about it, how these processes can help. And I want these electrodes to make up of gold. So if it is 50 nanometers, it means there is no wire which is of 50 nanometers we can use to make electrodes. So how we can make it, we can think about easily by using silicon processes. Some of these ones. So you have a silicon wafer, and then you can make a pattern into your computer, and you can transfer it with a process. It's called the pattern transfer. Okay, now it's so you can transfer that pattern, and then you can also use a CVD, chemical vapor deposition, to deposit gold on the surface. Okay, and then you etch part of the materials from there. In that way, at the end, you can have any feature on your surface. So this is just one example. And the ones I showed you, the nanopores, there's also, you can build those nanopores by using these processes. And you can also build the cantilevers. When we talk about the cantilevers, so those are hanging structures in nanometers. The same way, you have a one printed structure, and you can etch. For example, this is a silicon wafer, and you first print a structure on top of it, like 200 nanometer small wire, and then you just etch under the silicon printed area. So in that way, you can have a hanging cantilever, which you can use it for any sensing purposes. So why I'm giving you this information, so that you guys can feel some interest into learning these processes also, why these are important, and how they have applications into biotechnology in making different sensors. Okay. Unfortunately, we don't have the clean room here at FAU. But University of Miami and Florida International University, they have their clean rooms, so where you can do all these processes. So you need some specific facility to do it. And for my lab, we are building up a new facility, which is very nearby from here. It's room 50, close to a medical school, where we'll have part of these processes there, hopefully in spring. Where you can do photolithography, you can do part of deposition and other processes there. It will be a small clean room. So then you can do deposition, you can do pattern transfer. CMP is chemical mechanical polishing. So this is a process where you can polish or remove some of the material. So it's like once you polish, you remove and shine your surface. So the wafers, when you cut it, they are not very clean. So you use also CMP to clean it. And there are, it's just it's kind of sandpaper, but you have some chemicals in there, and you rub the surface to make it clean. So that's a CMP process, which is also used for many different applications. So ion implantation is, for example, you have a silicon, and you want to implant some ions into your silicon. Ions can be made of phosphorus or boron. So you make an ion, you hit it with the silicon, so it will just rupture the surface and go inside. So in that way, you can implant those phosphorus or boron or any impurity into a silicon wafer, and then you heal up that damage. So that's the ion implantation, and then you can package it. You can do other thermal processing which is needed. So once you do bonding, the whole device is ready. This is the general process outline, how you can use different processes to make and pick and dice any structure on the surface. It can be any microfluidic device. For example, if we talk about the microfluidic device, first we have to make a mask, like what you want to print, what type of channels you want to make. So you first design it into your system. You can use the AutoCAD or any other software where you can draw lines and whatever you want to. For example, if you want to make just the channels, so just make a line, and then another line, another, you make a pattern of it, and then you use a lithography where you can transfer that pattern onto your wafer. There is a process to do it. So now your pattern is transferred on the wafer, and then you can transfer that pattern from wafer to another polymer. So, and then you can stick that thing with the glass slide or something, and in that way you can have a microfluidic channel onto your surface. we'll go into in deep details how exactly to do it, but this is just general description. So generally speaking, you make a mask, and then you do lithography,